Okay, this is going to be a video on the law of cosines. So we've covered the law of sines, which is a bit nastier in terms of algebra than this one, so hopefully this will be a bit quicker. So I've got this little note up here. Wouldn't it be nice if the Pythagorean theorem applied to non-right triangles, or another way we can say that is oblique triangles? Law of cosines to the rescue. So law of cosines is basically adding this little correction factor to our Pythagoras, which is a squared plus b squared equals c squared. So let's start with an easy one. How could you prove that this triangle right here is a right triangle? So easy enough. If it is in fact a right triangle, it should solve our a squared plus b squared equals c squared. So let's go ahead and do that. 24 squared plus 7 squared is going to be equal to 25 squared, and that is 49 plus 576 is equal to 625. Boom. Yes, those are in fact equal, so it is a right triangle. No protractor needed, not that we use those really anymore. Okay, a little more interesting, let's look at this one, and this side 6 is supposed to be up there, but floated off. So how could we say that c squared might be bigger than a squared or b squared, or less than or equal to, without knowing anything or doing any calculations? And again, this is c because it's opposite angle c. This is b because it's opposite angle b, just for clarification. So I'm going to ask you to maybe pause and answer this in the Edpuzzle, but the reason is that this angle c here is obtuse. So it would make sense that the bigger that angle is, the bigger this angle, I'm drawing angle c here, so this is kind of close to right, the kind of more open you draw that angle, the longer this opposing side is going to end up as. So that would be one way we could do that. Now let's try to do this calculation and see how much we whiff by. So we've got 7 squared plus 6 squared is equal to our c squared, or we're trying to check if it's equal to our c squared. So that ends up as 49 plus 36, is that equal to 121? I think not. So we're actually off by a whole, let's see, what would that be? 36. So we missed by 36 units, whatever that is. So clearly our Pythagorean theorem is not gonna work out for us there. But let's move on to this number 3 here. Suppose that we know that this angle C, the one I'm coloring in here, is equal to 115.4 degrees. Let's calculate this here, and we'll get to why this is what it is. We can go over a proof in class. But let's calculate that. So 2 times our side A, which is 6, times side B, which is 7, times the cosine of angle C, which we were just given, is 115.4 degrees. Again, endless sirens, I apologize. So what that ends up as is, I've calculated this one out. You're welcome to plug it into your calculator, making sure you are in degree mode. We end up with 36.03, which, interestingly enough, is the exact same as how much we missed by. So I think I said at the beginning, this is our correction factor. This is kind of makes our Pythagorean theorem a little bit more robust. So if we added, or I don't know why I put degrees here, this is not in degrees, but rather in whatever units of length this is. But if we added this to our a squared plus b squared, we would have gotten 121. So, I mean, with a little fudge factor of 0.03, but close enough. So this clearly, this 2ab cosine of c is pretty useful for us. So going back to our right triangle up here, our 7, 24, 25, let's try to calculate that for our A, B, and cosine of C. So we've got a side A of 24, a side B of 7, and an angle C of 90 degrees. Now, maybe there are some enterprising folks among you that are going to realize that you don't really need to do the math here, but let's go ahead and do it. 7, 24, and cosine of a right angle, and another way to say that is pi. And if we think about our cosine of pi, that's 0, so boom, this ends up as 0. And that makes sense because if we're calling this AB cosine of C our quote-unquote correction factor, if it's a right triangle, you shouldn't need to correct at all. It is, in fact, a squared plus b squared does equal c squared, no correction needed. So let's try to come up with this, adding in this, this correction factor to our Pythagorean theorem to see if we can make it hold up under any case, under any oblique triangle. So we see this AB cosine of C, but let's make sure we know what we're talking about here in terms of making a generalized equation. So we had this triangle, and we knew that AB cosine of C, if we added that to our other side, we would end up with the correct answer. So AB cosine of C was in fact equal to our side C squared and we had to square A and square B. So A squared plus B squared plus 2AB cosine of C ended up as our side C squared. Now, I cheated a little bit. We needed to add this, but actually we are going to subtract it because this was a negative 36.03. So subtracting a negative, you can plug this in your calculator and see that this does in fact end up as negative 36.03 because this is in quadrant 2, 115 degrees. If you remember, your unit circle is going to be over here somewhere, so our result will be negative. So we need to subtract it because we're not going to add it. The result will be adding it. Subtracting a negative is the same as adding. But what we're really looking for here is this. Subtracting 2AB cosine of C equals C squared. So let's break this down. We've got two of the sides that we know, and then these two reappear here. So the first two sides minus 2 times those same sides again times the cosine of this angle is going to give us the correction factor, which will let us solve for the last side, or the last side of our oblique triangle. So let's use kind of a different example. If we wanted to solve for b squared, how might we rewrite this? Well, maybe this will be an Edpuzzle question and you've already solved this, but let's kind of see the form here. So we see the c squared appear on this side and the cosine of c, so it might make sense that we have a cosine of the angle b, and then the remaining sides on this one are going to be c and a, so c squared plus a squared minus 2ca. Does that form generally match the one above it? Yes, it does. So we've got the first side squared plus the second side squared minus 2 times those same two sides plus this cosine of the last side, which appears on the other side of the equation. Now, our first two sides are c and a in this one, so we've got c squared plus a squared equals 2ca, and then this cosine of the thing that, the cosine of the angle whose side appears opposite the equals. So that is the general form of the law of cosines, and you could apply that to any combination of a's, b's, and c's in whatever form they appear. So no special cases with law of cosines, and that is all we got.